You can hide me on stream.
Hello everyone. Welcome everyone. And today, post-COVID, we have rebooted our Mumbai Java user group, and we have our first session on algebraic data type plus pattern matching equal to elegant and readable Java code by Balkrishna Rawool, right? So Balkrishna is a passionate Java speaker, and he speaks on a lot of international conferences and Java user groups. So without further ado, I'll add Balkrishna Rawool.
Hey, hello. Thank you, Nishant. Thanks for the nice introduction. And yeah, really happy to be here at the Mumbai JUG event. I know that you have been looking to reinitiate the activities that are happening on Mumbai JUG, and I'm honored to be part of the first meetup of this. So really glad. And also it is especially important for me because I am from Mumbai. I started my journey as a Java engineer from Mumbai, so it is really it feels great to be part of this meetup and to be part of Mumbai JUG. So thank you for the introduction. Thank you for a great opportunity. And yes, today we will talk about algebraic data types, pattern matching, and we will see how we can use that to write elegant Java code. But before we do that, do you have any final words, Nishant, before I start with the presentation?
No, we can start with the
Okay,
presentation, right?
perfect.
Yeah.
Thank you. Let me share my screen, and you would need to allow. Oh wait, I think. Yeah. Are
Yeah,
you able
we
to
can
see
see.
the presentation, Nishant?
Yes, we can see your screen.
Okay, perfect. So, welcome everyone. Thanks for being here. Thanks for joining the Mumbai JUG Meetup. And in this instance, we're going to talk about uh, some features of modern Java, especially records and seal types and pattern matching. And we'll see how we can use those features to write readable Java code. Now, the title of the talk is Algebraic Data Types plus Pattern Matching equals Elegant and Readable Java Code. So basically, we will look at what algebraic data types are, what pattern matching is, and how can we combine these two things to create elegant and readable Java code. Now, the talk is actually divided in 4 parts. We will start with a problem, and then we will design a solution for that problem, and then we will implement that solution by using algebraic data types and pattern matching. In fact, let's say algebraic data types and pattern matching would be at the core of this of that implementation, but there will be some things around it in order to make that solution complete. And in this process, we will write easy to read and easy to understand code, or you can say if it is otherwise. But I hope we will be able to write easy to read and easy to understand code. Okay, so let's get started. But first, a very quick introduction about me. My name is Balkrishna Rawool. I work for ING Bank as an engineering lead. And I like to speak about modern Java. Java is really something that I'm passionate about. I'm doing that for many years. And the recent developments in Java are something that that I find really interesting. And these features, they motivate me to go and talk about these things. But also, um, I use Java on my day-to-day job as well, and then that gives me some perspectives that I want to share. Also, you can see the Twitter handle on this slide. If you want to connect with me, you can use that. Or I'm also on Blue Sky and other social networks, so I will share it at the end. Okay, so that's a bit of introduction. Let's start with the talk, and the first part is the problem. So I said at the beginning that we will start with a problem and then we will solve that problem or design a solution for that problem. So the problem here is actually a puzzle, and a puzzle that looks like this. Now, what we have here is we have a mathematical equation, and the numbers are replaced by letters. Here you see there are different letters, and we need to find out what are the numbers behind these letters to solve this puzzle. And each letter represents a unique number. For example, here E appears at 3 different places. So all these places, it will have a same number or same digit, but that digit won't appear anywhere else. So this way, we can try to solve this problem. If you try to solve this manually, you will soon realize that it's actually quite difficult to do that. Now we will see that why it is difficult and then how we can solve it. But before we move on, maybe a quick check in the audience. Have you seen these kinds of problem before? Nishant, have you seen such a problem before?
No, I mean, this looks quite interesting to me. So yeah,
Yeah,
looking
it
forward
is.
for
It
the
is.
session.
It is interesting. So let's try to analyze this puzzle, and then we see how we can solve it. So let's look at the rules or the requirements of this puzzle. Now, this is what the puzzle is. Now, these kinds of puzzles are also called as cryptarithmetic puzzles. And here, each letter corresponds to a single-digit non-negative number, basically a single digit, which is not zero, which is not negative. And then all letters here have unique numbers. So each letter, which is different, is basically a different digit. And letters placed together form a multi-digit number. For example, SEND forms a 4-digit number. MORE forms another 4-digit number, and MONEY forms a 5-digit number. Now, here in this specific puzzle, the letter M cannot be 0. This is actually quite helpful because this reduces the solution to 1, but we will see how it is useful and what can we do with it. Finally, the equality constraint, for example, send plus more, no, that has to be equal to money. So these are all the rules or all the constraints that we have. And let's now try to analyze the problem. We have 4 letters: SEND, MORY, and there are a bunch of rules or a bunch of constraints that are applied to them. For example, the first constraint is that each letter has 10 possibilities. It could be 0 through 9, except M, that we know because M cannot be 0. That's what the rules said. Now, if we try to look at all the possibilities that these letters can have, the values that these letters can have, then we will see that they will get a pretty huge number. But there are also other constraints that then reduce that number. For example, each letter has a unique value, right? And then there are more rules. For example, M cannot be 0, and send plus more has to be money. Now, if we try to see what are the possible solutions for each of these rules or each of these constraints, we'll see that for the first rule, we get 90 million possibilities. Then if we apply the second rule, which is each letter has unique value, we get more than 1.6 million combinations of values, which is still a pretty high number. If we apply the fact that M cannot be 0, which means M is 1, and then we get the number of possible solutions to 181,000. Now, 181,000 is still a pretty large number. So you cannot do this manually, but we can use computer. We can write a program to try this 181,000 times, and then we will have the program run and solve the equation for us. And finally, when we apply the final constraint, send plus more equals money, we will have our final solution or solutions. Now that is the aim to find here. Now, if you have these kinds of problems where you have a bunch of variables and then a bunch of constraints are applied to them, then you can use something called as constraint programming to solve these problems. Now, with constraint programming, it has a bunch of variables and a bunch of constraints that are applied on these variables. Wait, I want to hide this message, but I want to show this. Oh, you're still not hiding it. Okay. Anyways, okay. So in constraint programming, we have a bunch of constraints and a bunch of variables. And there are specific kinds of problems in constraint programming, which are called as constraint satisfaction problems. And these are called so because the idea here is to basically find a solution where all the constraints are satisfied. And in fact, that is exactly the problem that we are dealing with. We have a bunch of variables and a bunch of constraints. So constraint programming would be very useful for us to solve it. And in fact, in Java, we have a bunch of libraries that we can use to solve these kinds of puzzles. Like Choco Solver, JSolver, Optaplanner, or MiniCP. So these are the different libraries that we can use, and in fact, many more, to solve constraint programming problems. But for our problem, we are not going to use any of these libraries. What we are going to use is our understanding of constraint programming, and then we will use some of the Java features to solve the puzzle that we have. Okay, now what we said earlier was that if we apply all the constraints, we get the number of possible solutions to be 181,000, right? So if we write a program to basically try all these combinations, we will eventually have a solution. That is basically brute forcing a solution, and that is exactly what we are going to do. So how does our solution look like? This is the puzzle that we have. What we're going to do is we are going to write a component which will generate all possible combinations of values for all these variables. And we're going to call that component generator. Then we will have another component which will basically evaluate all these expressions, and we'll call that component expression evaluator. And finally, when all constraints are satisfied for a combination of values, we have a solution. Now we'll create a component called puzzle solver, which will check for all the constraints being satisfied. Now, if we put all these components in a picture, it looks like this. Now, what that means is we basically have a generator which generates all possible combinations of values. Then we have a expression evaluator which evaluates all these expressions, and then we have a puzzle solver which basically uses generator and expression evaluator to find a solution for our puzzle. Okay, so far what we have done is we started with the puzzle, we analyzed the puzzle, we saw what are the possible combinations, possible ways to solve it, and now we have some kind of high level design that we can use to solve our puzzle. Now, I hope you are still with me. Nishant, is there any question from you or maybe in the chat?
No questions so far. We can go ahead.
Okay, perfect. Thank you, Nishant. Okay, so far we have a high-level solution design for our puzzle. Now let's zoom in onto specifically, let's say, the expression evaluator part. Now there we are going to evaluate expressions. So let's see what we can do there. On the expression evaluator part, let's take an example of an expression like send, SEND. Now here, what we see is that it is composed of 4 letters. And let's say the values of these letters are small letter SEND. Then the value of the entire expression becomes S times 1000 plus E times 100 plus N times 10 plus D. Now, if we plot this value or plot this expression onto a binary tree so that the in-order traversal of the tree gives us this value, then it looks like this. Again, I'm only doing this to understand the different expressions. But if you're not able to follow, or if it is too quick, you can just ignore the binary tree part. But I will continue and then come to the conclusion, and at least the conclusion would make sense. So what we have here is we have a binary tree, and if you do in-order traversal of this tree, what we'll get is starting with the bottom left part, S times 1000 plus E times 100 plus N times 10 plus D. Basically, this expression we'll get. And if you pick any random node from this tree and then create a subtree with that node as a root, then the in-order traversal of that subtree will also give us a valid expression. For example, let's start with this plus. Now, the expression that we get is S times 1000 plus E times 100, which is a valid expression. Or this multiplication it would be N times 10, which is still a valid expression. Or if you take this D itself is a valid expression. And if you take 10 is also a valid expression. So basically, we have different kinds of valid expressions that we can create out of this binary tree. And if you look at all possible combinations, we get a grammar for these expressions. And that grammar looks like this. So what that means is, now this grammar represents all possible valid expressions, and it says that an expression can either be a constant or a variable, or addition of two expressions or multiplication of two expressions. And this grammar represents all valid expressions, but also any valid expressions can be expressed using this grammar. If the expression is invalid, you cannot represent using this grammar. And a grammar like this can be implemented by using algebraic data types. So let's look at algebraic data types very quickly. And then we will, in the end, use that to implement this grammar for our expression evaluator part. So let's look at algebraic data types. What are they? Well, these are the data types that are created by combining existing data types, mainly by applying algebraic operations. And there are two common categories, which are called sum types and product types. Now, we'll look at those in detail now, starting with product types. What are product types? So, well, in product type, each possible value of a new type has value for each of its constituent types. Now, as we said earlier, algebraic data types are types which are created by using existing types, right? By applying algebraic operations. So in product type, the resulting type that we get has value for each of the constituent types. For example, a point. A point has two coordinates, x and y. Now, in Java, you would implement that by using a record where you say record point has integer x and integer y. Now, here the resulting type is point, and point has value for each of its constituent types. So here point has two constituent types. Both of them are int, and therefore any instance of point will have two integer values, an x value and a y value. And because it has both these values, it is called a product type. Similarly, another example, so we have an address where address has a house number, a street, a city, and a country. You can implement that in Java by using a record like this. So here address becomes a product type of one integer type and three string types. So basically, anytime you see a record, you know that it is a product type. And if you want to implement a product type in Java, just use record. Okay, and now we talked about product types and sum types, right? So let's look at now what are sum types. In sum types, the resulting type, so basically each value of this resulting type is one of the values of its constituent types, right? It doesn't have all the constituent types, but only one of them. For example, let's say a shape can be a triangle, a quadrilateral, or a circle. Then you would implement it in Java using a seal interface. So here you have a seal interface shape, which can either be a triangle, a quadrilateral, or a circle. And then you have three record types, which are basically implementing the shape. They don't necessarily have to be record types, but in this case, they happen to be. So here, by implementing shape as a seal interface, what we are saying is that a shape can either be a triangle or a quadrilateral or a circle. So it cannot be more than one of these things. It cannot be a quadrilateral and a circle. It cannot be a circle and a triangle. Right? It has to be only one of these things. And that is what sum type is, because the instance of shape can either be an instance of triangle, quadrilateral, or circle type. So basically, shape here is the resulting type, and the constituent types are triangle, quadrilateral, and circle. So that's how you would implement a sum type. Okay, now we have some idea about product types and sum types, which are basically algebraic data types. Now let's look at pattern matching, because that will be the other feature that we will use in our solution. So let's look at pattern matching. What is pattern matching? So pattern matching is basically checking for a presence of a pattern in a given sequence of tokens. And in Java, now JDK 24 will be released in March, and it already has a lot of features finalized. But the important pattern matching features that we will use in this talk have already been finalized in JDK 22. So they are already available to us. And four main features that we will discuss here now, which will be very useful in our solution, are pattern matching for instance of, record patterns, pattern matching for switch, and unnamed patterns and variables. So let's start with some examples with pattern matching for instance of. So what we see here is an if statement. And what we're doing is that we're using an instance of expression. So we have object instance of point, and what that does, it checks if the object is of type point. But now we can also type a variable after this type, and what that does is it not only checks, so the instance of not only checks if the object is of type point, but it also creates a variable p. It also creates an object which basically is the same object but of type point, and then we can use p subsequently in the scope. So here we are using it to calculate squares and square root, so basically distance of the point from origin. Now, the other feature are record patterns. For example, here we again use instance of to check if the object is of type point. But here in this case, we deconstruct the point, because point happens to be a record which has two constant types, int x and int y. So we can deconstruct the point into x and y, and then we can use these variables x and y subsequently. So these two basically examples are equivalent. Here we use point p, here we use int x and int y. And if your record that you are using an instance of that happens to be composed of other records, then you can apply this deconstruction pattern recursively like this. So you can check if shape is an instance of circle, and then you can deconstruct the circle into a point and radius, and you can deconstruct point into x and y. So then you can use x, y, and radius afterwards. So basically you can apply the deconstruction pattern recursively. Okay, some more pattern matching features. For example, pattern matching for switch. Now, if we use pattern matching in switch, for example, shape, as we saw earlier, could either be a triangle, quadrilateral, or circle. So here, when we switch over shape, we can identify these three different cases, and for each of the case, we can write a branch. Right. So when we switch over the shape, which happens to be a sealed interface with three implementations, then we can write a case for each of those implementations. And the interesting thing here is that we don't need a default branch, because shape can either be a triangle, quadrilateral, or circle, and therefore all cases are handled here. You don't need a default branch. Basically, here we are calculating the number of sides for each shape. So for triangle it is 3, for quadrilateral it is 4, and for circle it is 0. And then the next feature that I want to talk about is unnamed patterns and variables. So basically, if you don't use a variable, you can replace it with underscore like this. So here in this case, we are not using these p1, p2, p3, p4. So we replace them with underscore. In fact, you can replace the whole thing with underscore like this. So your expression becomes pretty concise, and you can just say for triangle, the sides are 3, for square it is 4, and for circle it is 0. So basically, this and this are equivalent, and it is pretty concise. Okay, so we have seen a lot of pattern matching features. We have seen some other data types features. Now let's get back to the puzzle that we were solving. And maybe a check point here, if there are any questions, Nishant.
There is no question in the chat, right?
Okay,
Uh,
so can I
yeah,
just continue,
probably.
or maybe you have a question?
Yeah, I mean, so we are trying to solve some maths puzzle, right?
Yeah.
But if we want to apply this to a real life use case, right, or enterprise application, probably this question you can answer in the end.
Okay,
If you can
sure.
elaborate on more on that, right?
Yes, yes, for sure. I think that's a good question. So we are now trying to solve a puzzle, and we are using some techniques. How can we use them in a real life scenario in an enterprise context? Yeah, I'll get back to the question at the end of the end of the talk. Okay, so now what we have done so far, we started with a puzzle. We looked at some techniques that could be useful for us to solve it, and we also have a high level design. Now let's implement the design by using the techniques that we discussed, like mainly Azure data types and pattern matching. But let's define some solution steps. So how will we get from the high level design to the actual solution? So this is the puzzle that we started with. This is the high level solution design that we came up with. And now let's try to implement. Let's define the steps that we will implement. So here each letter corresponds to a single digit non-negative number. And that's the first rule that we have. Now, how we will implement that? We will implement that by using a type called variable, which will represent each letter. Then we will create another type called range constraint, which we will use to represent each possible value of variable, because each variable has a range. So we will use range constraint to define that range. And then we will create expression type with evaluation function, because we want to evaluate each expression. And then we will create a type called generator, which will generate all possible combinations of variable values. And then we'll create more constraint types, because there are some constraints which are still not satisfied. For example, all values must be unique. And for that, we'll create unique values constraint. And then we have another constraint, which is equality constraint must be satisfied. For that, we will create equality constraint. And finally, the final constraint that we have is that puzzle solver needs to use generator and expressions to find solutions. So basically, when all constraints are satisfied, we have a solution. And now for that, we will create a puzzle solver, which will use generator and expression to solve it. Okay, now these look like pretty, let's say, reasonable steps in order for us to solve this puzzle. So yeah, let's start with the implementation. And now I'm going to switch to IntelliJ, and then we'll implement the solution that we have discussed so far. So let me get back to the steps, because the first thing that we will do is we'll create a variable type which will represent each letter. So I'm going to head over to IntelliJ.
Balkrishna,
You're able to see
before
IntelliJ,
going
right?
on to solution, right? We have a two question. One is
Yeah.
from Jiten.
Mhm.
Which cases unnamed variable helps?
Yeah. So, well, first of all, good to have you, Jitin, in the chat. It would have been nice to have you also on the stream. But a good question. I think unnamed variables, right? We sometimes you have, for example, a method has certain arguments, and you don't use all of those variables in the implementation of the method, in the body of the method. So in that case, you can be explicit in replacing the variable name with underscore, and by that you are saying that I don't intend to use the variable. So you eliminate the chances of accidentally using it. So if you use it, then compiler will say that you shouldn't be using it, and so in those cases it helps us. I hope that answers the question. Are there more questions, Nishant?
Yeah, and we will take one more question from Coding Cloud. He's asking, this recursive internal pattern matching looks almost close to Scala.
Yeah.
Does it mean Java now has a Scala-like pattern matching as well?
Yes. So, and that is actually a very good observation, because I had the same observation as well when I saw pattern matching. But pattern matching is used in many languages, including Scala. In Scala, pattern matching is very, very powerful, and it is used quite often. And I'm actually happy to see that it is available in Java as well, because it helps us to write readable, elegant implementations. I don't think all features which are supported in Scala are now supported in Java, but under the project Umber, we will have more and more pattern matching features being supported, and that can always improve the language. And I'm not sure if their intention is to go towards Scala, but at least to support Java with more and more pattern matching features. That way, us as application developers can write code which is easy to read and easy to understand. But a very good question and a good observation. Nishant, are there more questions, or can I continue with the
No, we
implementation?
can continue and take those in the end now. Yeah.
Okay. We'll take other questions in the end. In terms of time, I think we have half an hour roughly from now. I think that should be enough for the implementation and the last questions. Now I'm gonna do some coding. For that, I'm gonna just put my mic a bit aside. I hope you can still hear me, Nishant.
Yes, we can hear you properly.
Okay. And I am sharing my IntelliJ screen. Are you able to see IntelliJ?
Yes, we can see your IntelliJ.
Okay. I think it is too small, right? Let me increase the uh, um, font a bit. Let me create something. We want to create a variable type, so a record variable. Are you able to read this, Nishant, or shall I
Yes,
make it
yes.
bigger?
Yeah, we can read it.
Okay, perfect. Then I will keep this. Okay, the first thing that we said we will do is we will create. Okay, first thing is create variable to represent each letter. So let me do that. This is the variable type, and to represent each letter, we need the name of the letter. So we'll call it string name. And then the next thing is to create a range constraint to represent possible values of a variable. For that, I'm going to create a record here, range constraint. And range constraint basically represents a range, so it goes from a certain value to certain value. And I actually created this record inside this record variable. And the reason to do that is because this range constraint is only used in a variable. Only a variable has a range, and that's why I created as an inner type to the variable type. And I'm going to use it here because a variable has a range. There you go. So a variable has a name and a range. Then the next thing is create expression type with evaluation function. And if you look at the grammar, so let me quickly move on to show you the grammar for expression. So what we earlier discussed is that an expression can either be a constant or a variable, or addition of two expressions or multiplication of two expressions, and it cannot be anything else, right? So expression can either be one of those four things, which means it is a seal type. So an expression is a seal type of these four types, and that is exactly what we are going to do. Sorry, an expression is a sum type of these things, and we are going to implement this sum type using a seal interface. So let me create a seal interface, new interface expression, and let's make it sealed. And it will have four implementations as we discussed earlier. So I'm going to use records for the implementations. So first is a constant expression. For that, I create this type const expression, and constant expression has a value because it is a constant value, and this implements expression. And then we have a variable expression. I'm going to call it var expression, and variable expression has a name because each variable has a name. And then we have addition expression. Addition expression has two expressions, which is addition of those two expressions. So we have expression left and expression right. And then we have multiplication expression. Expression, which again has a left and right sides. So this is our expression type, and that represents this grammar. Okay, and then we said we are going to write an evaluation function. So let me create a static integer evaluate. And in order to evaluate, we need an expression to be evaluated. So let's call it expression, and then we need values of the variables. So let's say we get them in the form of a map with string to integer. Integer called values. So basically, the idea here is this function, which is a static method, will evaluate this expression using these values, and it will return the evaluation of this expression. And because this expression is a seal interface, it is very handy to simply switch over this expression and write the implementation. So, and with IDs like IntelliJ, we can very easily create these branches because this expression can be one of those four types, and just it simply gives you these four cases. And I normally like to put them in the order that they appear here in their definitions. So I'm just going to move these branches a bit so that they are in the same order as they are defined. For constant expression, we have a value. And the evaluation of constant expression is simply that value. For variable expression, we have name. And then basically the evaluation of a variable expression is simply looking up the value inside this values map for that name, because this gives you a map of variables to their values. So if you simply look that value in here, you can get the value of this expression. Now, addition expression has two expressions, right? Left one and right one. And here, basically, the evaluation of addition expression is evaluation of the left-hand side adding to the evaluation of the right-hand side. And then for multiplication expression, it is actually very similar to addition expression, with the only difference is instead of addition, we use multiplication. So there you go. We actually have our evaluation function written. And let's take a few moments to see what we have done here. So we have this expression implemented as a sealed interface, and then we implemented this function evaluation by using pattern matching for switch. Now, the advantage of doing pattern matching for switch, firstly, is that because this expression can be one of these four types, we only need these four cases and we don't need a default branch, because these four cases cover all the branches or all the possible scenarios that this expression can have. And also, let's say if we miss a certain case. So by implementing this as sealed interface, we are saying that expression can be one of these four types. Let's say in our switch expression, we miss a particular branch, then compiler can tell us that, hey, we are missing that. So this is the advantage of implementing sometimes as sealed types and then using them in pattern matching for switch. So if you miss a type, compiler helps us to tell that, hey, we are missing something, and then we can add that branch or that case. Let's say if we have one more addition. So later on, we want to expand this expression type with, let's say, division expression. And now we have added an implementation here, but all the places where we used this expression type, namely with a switch expression, at all those places, now this case is not handled. Therefore, compiler again tells us, it helps us in identifying all the places where we are missing this branch, and it says you are missing something and you need to add that. So we could again add the missing branch, and then the compiler will be happy. So this way, using the sealed interface helps us to let's say expand our implementation. And this goes further. Pattern matching is very powerful. In fact, here we have identified all these cases for this switch depending on the type of the expression, but we can even be more specific on the case that we want to handle. So let's say we want to handle a division expression case where this is a dividend, and our divisor, which is the right side, is a constant expression which has a value, or we call it divisor, and we want to identify a case when the divisor is 0. And in that case, let's say we want to throw an expression or throw an exception, throw a new let's say arithmetic exception saying divide by 0 or something. Let's say this is what we want to do now. So basically what we have done here is we have identified a very specific case. We implemented that by using pattern matching, and then we write the implementation for it. So this way, reading the code becomes really easy. So basically we are identifying a division case here where the divisor is 0, and in that case simply throw an exception. So this way, well, first of all, when we use when keyword to identify or implement a particular scenario, we call that guarded patterns, and guarded patterns really help us to write a very readable implementation for the scenarios where we are using sealed interfaces. Okay, in our case, we don't need this and this. I just wanted to add those to show how powerful pattern matching is. So let's move on to the next bit.
Balkrishna, we have one question related
Yes.
to this, right? So
Yeah.
Zainab ji was having that question.
Uh-huh.
What is branches in switch pattern?
Yeah. So basically in switch expression, all these things that we identify here with case, these are all called branches. So if you miss something, then the compiler will tell you that this switch does not cover all possible values. We can add a default branch, or we can add a specific branch of multiplication. Basically, these are all branches. Anything that you see after case is a branch.
Yeah.
Okay, Nishant. Hope that answers the question. And if there are more questions, just interrupt me. No problem.
Sure.
Okay, then we have implemented the expression type with the evaluation function. The next thing is generator, and generator should generate all possible combinations of variable values. And for that, we have a generator type here, which is already implemented. Again, because generator is not the core of this talk, that's why I have it already implemented. But it is an interesting implementation. What generator does is it is a record which takes a list of variables and an indication whether we want unique values or not, and it gives you with this with the help of this function combination a list of all possible combinations of values. And it uses depth first search. It's an interesting implementation. I will share the link to the code at the end so you can take a look. But for now, I mean, it is not a core, so I have left it out for this talk. You can take a look later. Okay, after generator, then we need a couple more constraints because not everything is covered. Now let's implement these two constraints: unique values constraints because we need unique values, and secondly, equality constraint because we want cent plus more to be equal to money. And these two constraints are used in the puzzle solver. So I'm gonna create a sealed interface for those and put them inside that, basically implementing the sealed interface. And why I'm using sealed interface, we will see that a bit later. But let me create that first. Let's call it a puzzle constraint. It is going to be an interface, in fact, a sealed interface, and it will have two implementations: record unique values constraint, implements puzzle constraint, and then we will have to do equality constraint, which implements puzzle constraint. And the equality constraint requires two sides which need to be equal, right? So it requires two expressions, left expression and a right expression. And so this represents the constraint that left and right expressions are equal. Now, when we implement a sum type like this by using a sealed interface, we can also add specific behavior to each type. In this case, we want to add some behavior to the equality constraint by adding a function, let's say public boolean. So it represents boolean, and the function is called holds true for. So what it does is it checks if this equality constraint holds true for a certain set of values. And I'm going to use a map here again, going from string to integer, called values. So we'll check if this constraint holds true for these values. And this would simply be an evaluation expression dot evaluate. So we'll evaluate the left expression with these values. And let me do a static import for this. We will evaluate the left hand side for these values, and then we will evaluate the right hand side with values. And if they are the same, then that means this constraint holds true for these set of values. So this way we can also add specific behavior to a particular type in the sum type. Okay, and why I'm using sealed interface, we'll see that in a bit. And then the last thing is puzzle solver needs to use generator and expression evaluator to find solutions. And I'm going to create a record called puzzle because that will represent our puzzle. And if you remember the one of the slides from the beginning, the puzzle that we have is a cryptarithmetic puzzle, and it can be solved using constraint programming. And in constraint programming, what you have is a list of variables called variables and a list of constraints. Let's call them constraints. And our puzzle is also a constraint programming puzzle. And when you have a puzzle, what do? You solve it. So that's what we will do. We will solve this puzzle by using this method. And let me implement this in a bit. But before that, let's imagine we have this solve method implemented. And then the way to check that is to write a test method for it. Let's create a JUnit test. We call this test solve. And what this method does is basically tests if the puzzle solve method is performing okay or not. For that, basically we will use this to solve our original puzzle. For that, we need a bunch of variables. So I'm gonna create these variables here. So what that means is we have these these eight variables: S, E, N, D, M, O, R, Y, and they are going from 0 to 9, except M, which is going from 1 to 9. And then you have these variables. I'm going to create new puzzle, and new puzzle will have a list of variables and a list of constraints. So a list of variables which are S, E, N, D, M, O, R, and Y. And then we will have a list of constraints, which are basically two constraints. So first one is a unique values constraint. Let me do a static import for it. And we need an equality constraint, which somehow represents the equality that send plus more is equal to money. Okay. Okay, now that we have this part implemented, so now I can go back to the puzzle type. And I wanted to do this before because I want to also highlight the fact that puzzle takes a bit a list of constraints and a list of variables and a list of constraints. Okay, once we have this, let's go ahead and implement the puzzle type. So how do you solve a puzzle? We create a generator. So let's say we have a variable generator, which is a new generator, and generator requires variables and values. We have variables. We need the indication if we want unique values or not. So let's create a variable here, unique values. And we know whether we want unique values or not by looking inside the constraints. So if the constraints has constraints dot let's say any match, that one of the constraints is an instance of unique values constraint, then we know that we need unique values, right? So this is how we know that we need unique values, and then we can use this in here to get the generator. So we do generator.combinations, we get all the combinations, and then we loop over them. So for a set of values in generator combinations, we will check if one of these combinations is a solution values, and if it is a solution, then we will do something with it. Okay, but how do we know if a given set of values is a solution? Well, we will know that if all the constraints are satisfied, right? So we'll do constraints.all match, and then we'll check that this constraint is satisfied. So this way we'll know that the specific constraint is satisfied for these values. And when we know that, then basically all the constraints are satisfied and we have a solution. Now, how do you know if a constraint is satisfied? Now, this is where we will use the fact that puzzle constraint is a sealed interface. So we will simply return a switch over this constraint. And if we know that this is a seal type, and therefore we can add these branches, we can add the let me put them in the order that they appear. So first, the unique values constraint. And unique values constraint is satisfied. Well, it is already satisfied because we are looking unique values constraint here, and we are passing the generator whether we want unique values or not. Therefore, this is already satisfied. So I can simply return, I can simply return true here. And now in this case, I'm not using this variable. So I will replace this with underscore. That's the unnamed patterns and variables. For equality constraint, let me do a static import for this. And we know that equality constraint is satisfied if we can do equality constraint dot holds true for values. So this way we have it satisfied. And now this code becomes like easy to read. It reads like a constraint is satisfied when it is either a unique values constraint or it is an equality constraint which holds true for these values. So your code becomes readable. Now, if you have a solution, we simply return the solution here. That means we need to change the return type. And if we don't find a solution, we simply say throw new legal state exception saying no solution found. Okay, so we have puzzle implemented. Let's go ahead and implement the puzzle test. So here we will gonna just solve this puzzle, which will give us a solution. And now we are going to implement this equality constraint bit. But before I do that, I want to go to expression and add a bunch of methods. Call them expression static methods. So these are 4 methods which simply give us new instance of each of these expressions. So constant variable addition and multiplication. And these are useful or handy in implementing this part. So equality constraint is basically equality of these two things. And this is nothing but an addition of send and more. Let me import this and do a static import for this. And this send is actually a 4-digit number formed by using these 4 letters, right? So this is a number created by using SEND, and this is also a number created by using MORE, and this is a number which is created by using MONE and Y. Now let me implement this create number method. I have it already implemented. So basically it uses the fact that these are single digit numbers and you can just go from left to right multiplying by 10 and adding the next number. You can look at the implementation. It's not, again, not that difficult. Okay, and then once we have a solution, let me quickly do a good assert for it. So assert equals. So I want to make sure that this part, which is basically the left hand side, evaluates with this solution to the right hand side, which is this money, with our solution. And this is a good assertion because it basically checks if the puzzle is solved or not. And then after this is done, I want to actually do a pretty print for our solution. So the solution gets printed to the console nicely. And again, this is a simple method which just basically prints the thing on the console. Okay, I think I have everything here. Now let's run this test solve and see if it solves the puzzle or not. Okay, we have a solution here. So basically the puzzle that we started with, we have it solved. And again, the aim is not to solve the puzzle, but the aim is to look at this part, which is basically the core of our solution, the expression type. So what we did in the implementation of the expression type is we used algebraic data types. We use some types for implementing the expression itself, and we used record types or product types for implementing the various implementations of this expression. So we use algebraic data types to implement the data model for expression, and we use pattern matching to implement the behavior. And in that process, it made the code easy to read and easy to understand. That is actually the core of this talk. Now let me get back to the presentation with the puzzle being solved. So what we did in the process is that we kept data and behavior separate. So basically, this part is the data part and this part is the behavior part. So we kept data and behavior separate, and we used algebraic data types which helped us to model the data. So basically implementing data, and that we did by using algebraic data types. And it is done in a way that only valid states are allowed to exist. And then we use record and seal types to implement product and sum types, basically for defining the data part. And then for implementing the behavior part, we use pattern matching. So pattern matching features helped us in implementing the behavior or the functions that operated on that data. And this style of programming is known as data-oriented programming. So in data-oriented programming, it basically encourages us to model data as immutable data and keep the code that embodies business logic, like the functions, separate from the data. And this is actually a pretty a big topic. and it helps us to write readable code. Basically, using Algebraic data types and pattern matching enables us to do data-oriented programming, and data-oriented programming enables us to write elegant and readable Java code. And as I said, this is a pretty big topic, and for that, there's a lot of material that can be read, and I'm just gonna share a couple of links here. There are a couple of articles, one from Brian Gates, the Java language architect at Oracle, and Nikolai Parlak, who is the developer advocate at Oracle. But if you don't get these links, you can get this link, which is basically a link to the source code that I just showed you, and also it contains the links to those two articles, so you can get them as well. And you can find me on Blue Sky, Twitter, GitHub under these handles. So yeah, that's all I had to show you. Basically, the idea was using data types and pattern matching to do data-oriented programming, which enables us to write elegant and readable Java code. So
Thank.
that's it, Nishant. Are there any questions? Let me put this.
No, I mean, yeah, thank you for great session, right? It was interesting to read some of the, new Java language features, right? So thank you for that great session. And we will have just many more such sessions in future. And monthly, we plan to have one session, right? So definitely looking forward to having you again in near future, right?
Yeah,
And
thank you, Nishant,
yeah,
for the
and
opportunity. Yeah. And I just wanted to say a couple of things. One is, I think we still haven't answered the question that you started with. It is about, so we use some features to solve some puzzles, but how can they be used for
yeah,
enterprise applications, right? So basically, any enterprise application or any big application is basically composed of smaller puzzles, right? Smaller problems. So if we apply these techniques to those smaller bits, you can make the bigger problem solve with these elegant ways. And I can elaborate more on these things. Just reach out to me on these handles, and we can do that. Thanks for the opportunity, Nishant and Jiten and the entire Mumbai JUG team. Thank you for having me, and it was great to interact with you. But also reach out to me afterwards. Thank you,
yeah.
Nishant.
Yeah, and just closing mark, like if you have any sessions or topic that you would like to present, feel free to reach out to us, right? Follow Mumbai Jug on LinkedIn, Twitter, right? And Blue Sky, right? So please follow, please send if you are interested to, deliver any talks to us, right? At Mumbai Jug platform. We welcome you. And with that, I'm going to stop today. Have a great day and have a great weekend. Bye.
Thank you. Bye bye.